So back to the subject of central angles. Suppose that you are dealing with a circle. Radius of the circle will be r. Central angle will be referred to as theta. There are two additional quantities that we're interested in calculating here. One of them is referred to as s, and s is referring to the length of the arc that is subtended by angle theta. That is to say, if this were a slice of pizza right here, s would be referring to how long the crust is. Additionally, we have the area of the associated sector. The sector would be like the slice of pizza itself. So this is area of the associated sector. There are formulas for both of these that you're going to want to familiarize yourself with. Now, S kind of came from the definition of what a radian was, but S is going to be equal to r times theta, where theta is measured in radians. Now, in the event that theta is given to you in terms of revolutions or in terms of degrees, it'll be your responsibility as the student to convert it to a radian measure. The area of the associated sector is going to be equal to 1/2 times theta times r squared, where again theta is going to have to be measured in radians rather than in terms of degrees or revolutions. Now, I do want to point out one thing regarding this formula, though. Excuse me. That if we were to refer to the entirety of the circle, if theta is equal to 2 pi, which again is referring to 1 revolution, then the S formula would become r times 2 pi, or reordered slightly, this would be 2 pi r, which we recognize as being the circumference or the entire perimeter of the circle. Additionally, the area formula would become 1/2 of theta, which is 2 pi, times r squared. The half and the 2 will cancel each other out to leave us with pi r squared, which hopefully we all recognize as being the area of one complete circle. Now, in addition to introducing these formulas, we can also talk about the potential of having these quantities change over the course of time. These introduce the concepts of angular and linear velocity. So this is saying not only do you have a circle, but you actually have an object that is traveling in a circular path. So over the course of time, as it travels in a circular path, it will create an angle, and r and s. The new factor that we can bring in here is going to be time. Time could be measured in seconds, minutes, hours, whatever units you prefer. So first concept that we have is referred to as angular velocity. Angular velocity is notated by the Greek letter omega. Now, angular velocity is going to be very straightforward. How big is the angle that you are creating, and then divide by time. When we think of most speeds or velocities, chances are pretty good it's a distance per unit time, like meters per second, miles per hour, feet per second, those sorts of things. Now, angular velocity works the exact same way, but rather than a distance, this is going to be measuring an angle. Once again, we're going to want theta to be measured in terms of radians rather than in terms of anything else. The linear speed is going to be dictated by the letter v, and this will be the actual distance per unit time that you're traveling. The distance that we're traveling is that distance s along the exterior of the circle. However, we do have a fancy new formula for what s is equal to based on what I have up here. So what I could do is make a substitution on the s and refer to it as r times theta divided by time. Now, that in mind, we also just introduced this idea of angular velocity. So if I take a radius times theta over time, that would give me a radius times omega. Now, technically, the units that you would see here would be a distance times radian per time, but usually when we think of a linear speed, we think of distance per unit time. Radians are known as a dimensionless measure. Include them if it makes sense to, don't include them if it doesn't make sense to. We'll go over some examples in the next video.